Good morning, everyone. My name is Amir Hassan, and today we'll be talking about the transition to electric vehicles and its effects on overnight power generation in the New York Independent System Operator region. So let's get started. With rapid succession, California, New York, and the European Union have all put forth regulations banning the sale of vehicles using internal combustion engines that are powered with non-renewable petroleum-based fuels by 2035. In the coming years, we can expect several other states and nations to adopt similar policies in a move to decarbonize one of the largest parts of the transportation sector. This begs the question, how will the transition to electric vehicles affect the demand for overnight power generation and the energy sources needed to meet it? When considering other decarbonization efforts in the energy sector, this question becomes even harder to answer. Despite this, it is a question that will need to be answered to maintain the ease of mobility that the world has grown accustomed to over the past century. Reducing the ability to transport people and goods would have devastating effects in the world's global economy. Let's talk about current evening and overnight power generation sources. Efforts to decarbonize go way beyond the transportation industry. There's increasing pressure to move to zero-emission power generation. There's decommissioning of polluting plants, coal, natural gas, combined heat and power. Nuclear is being decommissioned due to citizen sentiment, even though it's zero-emission. And there's undisputed reliability and stability at all hours of the day with these kinds of plants. Renewables have lots of pros, but also lots of cons. Renewable sources such as solar and wind cannot produce consistent power in the same manner. The power generation by photovoltaic panels is nearly zero in the overnight hours. In many residential settings, batteries are often used to store excess power generated for use in the evening, when energy demand often peaks as people return home from work and school. This imbalance between home energy use during the peak sunlight hours and peak power consumption presents a significant challenge. Chemical storage in the form of batteries is not a perfect solution. The precious materials used in batteries, such as lithium, are difficult to obtain and are done in environmentally damaging ways. Battery production also has environmental concerns. Furthermore, batteries degrade with time as they are cycled between charge states. Onshore and offshore wind power generation varies by the ebbs and flows of wind currents. It is clear that changes to the electrical grid will be necessary to meet this increase in demand at critical hours. A common solution used today is hydro-pumped storage. In this application, water is pumped up to a reservoir in the off-peak hours when power is cheap. During the daytime, this water is released, converting its potential energy into rotational energy for use in a generator. Changing the time where this power is released can help relieve grid strain during these hours. There are also promising developments in vehicle-to-grid integration to optimize charging by spreading charging into batches of cars. Other technologies such as fuel cells, which provide consistent baseload operation, and thermal energy storage are also worth investigating. To understand the current landscape, we must first obtain general figures which represent the existing power generation for the New York Independent System Operator region. On the left, you will find a map of the different regions. On the right, you will find a table of the integrated real-time load data in 2021. The total power used by the state in 2021 was about 152 million megawatt hours. Now, to consider the evening and overnight hours, we will narrow this range down to data points between 5 p.m. and 5 a.m. The integrated real-time load data for this time range can be found with the relative percentage to the total generation beside them. As you can see, about half of the entire power generated for New York at this critical time range occurs during the evening overnight hours. The impacts of nighttime charging of electric vehicles will certainly affect this balance and will be explored in a later segment of this video. Well, how many vehicles does New York have? The New York State Department of Motor Vehicles reports that there are 11,237,604 registered vehicles with New York plates as of November 2nd, 2022. The state also tracks the number of vehicles with out-of-state plates. Out-of-state plates account for about 1% of all vehicles in the state. To simplify our efforts, we will neglect vehicles with out-of-state plates and assume they are not charged within the state. This assumption will result in some error, as a non-zero quantity of vehicles with out-of-state plates will be charged in New York. To account for the current fleet of EVs, New York reports there are about 77,000 vehicles as of November 2nd. However, this is such a negligible amount, it makes up only 0.68% of all vehicles registered here, so we will also be neglecting it for our purposes. Now that we've gathered the necessary data about the current state of vehicles in New York, we must look ahead at electric vehicle projections. Arvind Jaggi, a senior economist for New York Independent System Operator, projects that full EV replacement of light-duty vehicles, such as sedans, coupes, small SUVs, would peak around 2051 with different adoption rates provided. You can see the graph on the right illustrates the projection based on number of vehicles and annual energy impact in gigawatt hours for the three different rates. In order of high, medium, and low rate of adoption, the number of electric light-duty vehicles in 2051 would be about 7.5, 6.2, and 5.1 million. The energy impact would be about 24,000 gigawatt hours, 21,000 gigawatt hours, and 15,000 gigawatt hours, respectively. Light, medium, and heavy-duty trucks would see their peak a little bit past 2051 because the technology has not matured yet for those kinds of vehicles. They also would make up a much smaller version of the total fleet, of course. However, they would have a higher overall annual energy impact relative to the fleet size and additional vehicle weight. This is another graph generated by New York ISO. You can find that the peak energy usage in gigawatt hours would be about 32,000 gigawatt hours in 2042. Another important detail regarding impacts to the grid is the time at which charging occurs. Most charging occurs between 8 a.m. and 10 p.m. However, the type of charging varies based on the time of day. During the morning hours, level 2 fast chargers at workplaces and public spaces, as well as DC fast chargers, dominate the overall charging profile. However, they are dwarfed by home level 1 and 2 chargers after most people start going home from work in the evening. The plot on your right illustrates this very well. Light and medium-duty trucks see a similar charging profile as light-duty vehicles. However, heavy-duty vehicles usually need a midday recharge due to their extra weight. On the right, you can find the bus profile, where they take advantage of the non-rush hours during midday to get a recharge. After establishing the energy impacts and timeline for the replacement of the vehicle fleet, the current power generation sources for New York should be examined. The United States Energy Information Administration reported that New York generated about 125 million megawatt hours of electricity in 2021. This was about 17.8% less electricity than it actually consumed, which means some of this power had to be bought from outside the state, but the way electricity markets work, some of that excess power that New York generated in the moment definitely had to be sold to other regions to balance things out. Moving forward with clean energy, New York's power sources have dramatically changed in the last few years as it tries to meet the requirements of recent legislation known as the Climate Leadership and Community Protection Act. This law sets ambitious targets for reducing carbon emissions and increasing the use of renewable sources of energy. It requires 70% of state electricity to come from renewable sources by 2030. By 2040, 100% of electricity generated must be from carbon-free sources. As you can see with the picture on the right, there are several renewable projects already planned, such as distributed solar, wind, and battery storage. So, what does New York's power grid look like right now? Well, 37.2% of all power generation comes from natural gas. Coming in second place is nuclear power, which makes up 34.2% of all power used. About 28.3% of this power also comes from renewables, with 25% being hydroelectric, thanks to the Niagara Falls and the dams in the north of the state. Currently, about 50% of all power generation in New York is zero emission, so we're on a good track. The figure on the right can show you more details. What does a complete transition look like? Using the data in Jaggi's Gold Book, let us see how much power was used in New York in 2021 for transportation. To calculate the total energy used by vehicle class, the following formula was applied for each vehicle class and their respective totals. You take the average vehicle miles traveled, multiply by the energy use per mile, multiply that by the number of vehicles in that respective class. The total energy use of a pure EV replacement of all vehicles in New York using 2021 figures would be approximately 78 million megawatt hours. This represents about 52% of the total electric load that New York used in 2021. When compared to the evening and overnight electric load that we calculated, an all-electric vehicle fleet would use over 4 million more megawatt hours than was consumed between 5 p.m. and 5 a.m. This presents a significant challenge for power operators, utilities, generators, governments, and the citizens. New York would be in no means prepared to handle a 52% increase in electric load without significant additions to its power capacity, renewable or not. So, how will we fix this problem? Well, we now must consider the power sources that will replace or supplement these fossil fuel power plants during the transition to electric vehicles. As previously mentioned, New York intends to add over 30,000 megawatts of renewable energy generation assets by 2035. This includes 16,000 megawatts of distributed solar, 6,000 megawatts of battery storage, and 9,000 megawatts of offshore wind. Of course, with renewable energy, consistent power generation is not an expectation. However, using historical data, we can simulate the expected power that New York could expect over the course of 1 year. This will be done using NREL's System Advisor Model program. Beginning with distributed solar, I used the PV Watts No Financial Model. I selected Albany, New York as a middle ground area for the state. A nameplate capacity of 60 million kilowatts was used, and all other values were left default. The simulated energy generated for the first year was about 19.6 million megawatt hours at a capacity factor of 14%. On the left, you can find a plot of the monthly AC energy across 1 year. You can see the months of March through about September have the highest generation possible. And on the right, you will find a heat map of all the power generated as well across 1 year. From beginning of the year to the end of the year is on the horizontal axis. From the beginning of the day at midnight to the 11 p.m. hour at the end of the day, you'll find on the bottom. And you can see kind of that middle band. And that middle band shows you where power is peaking. So you can see the red is the highest power generated. And in the nighttime hours, 20 to 24 and 0 to 5 a.m., you see almost zero power generated. Now considering offshore wind, I selected a location of the offshore Sunrise Wind Farm and used the Wind No Financial Model. A hub height of 160 meters was selected. And for the most energy density at the minimum number of turbines, the NREL reference 18 megawatt wind turbine was used. It has a rotor diameter of 263 meters. And in order to meet 9,000 megawatts, as per the state, 500 wind turbines would be needed. Due to limitations in the model, I can only simulate a maximum of 300 turbines, so instead I calculated 250 turbines to get half of the value and then doubled it. I also enabled the uncertainty model to account for variations in wind speed, and the resulting AC energy for the first year was found to be about 35 million megawatt hours at a capacity factor of 44.6%. Interestingly, compared to the solar, you can see August had the lowest wind generation compared to August being almost the highest for solar. And on the right, you'll find this heat map where you're generating power at many hours of the day because, frankly, it's wind, not sun. So you can get it no matter what time of the day it is. So that's just something to be interested about. So, coming down to our results, as we found in the analysis, to meet a full replacement of the vehicle fleet with electric vehicles, New York would need to generate approximately 52% additional electricity of its general baseload, based on my calculations. However, the New York ISO prediction was about 33,000 gigawatt hours. This is quite a significant difference. In fact, it makes up to be about a 138% difference between our two values. I also plotted the load curve and load duration curve for 2021 for reference. It can be quickly observed from the load curve that peak loads occur between the months of May and September, where temperatures are high and the use of electric air conditioning is necessary to cool down homes and commercial buildings. However, during those months, we also see the largest spread in load, where the temperature delta as a result of overnight lows will see much lower AC use. Summer loads reach minimums similar to the rest of the year because less artificial lighting is necessary during the longer sunlight hours. The spread during fall, winter, and spring in load is also far smaller than during the summer. On the right, the load duration curve shows the greatest of loads, approximately 20,000 to 32,000 megawatt hours, occurs for about only 10% of the year. There's a sharp drop-off from the highest of the loads, and the rest of the plot has a much shallower negative slope between 10% and 100% of the total time in 1 year. If one desired, you can make a linear approximation between 10% and 100% with relatively minimal error. When considering additional grid capacity, one must also consider the seasonal impacts on the grid. As you can see in this previous picture, the blue line represents the winter peak and the green line represents the summer peak. EVs use more energy in the winter. That's because the batteries can't hold the charge as well. So that is just something that must be accounted for. Moving on, the results of the models simulated using the System Advisor model found that with current expected renewable capacity, we will add at least 55,000 gigawatt hours to the grid by 2035. Based on this value, assuming all other factors stay equal, using New York ISO's predicted load estimate of 33,000 gigawatt hours, New York would have room to spare, and they can handle the EV replacement just fine. It even gives them additional room to spare for decommissioning of the polluting plants. However, this does not meet the EV needs if my estimation is used. Several factors can impact this, and we'll be discussing it in the next slide. To conclude, the discrepancy between my number and the New York ISO estimate is significant. There are some factors that I did not consider. Efficiency improvements as the technology improves, improved battery chemistries, higher voltage charging infrastructures, or reductions in motor losses. Overall, these would all reduce the kilowatt hours per mile up for every vehicle class. In fact, I'm optimistic. According to the Vehicle Technologies Office at the Department of Energy, the median vehicle range of a light-duty EV is about 234 miles with a maximum of 405 miles. This number is growing almost every day. Now, assume the average person uses their vehicle about 40 miles a day, 5 days a week, about 200 miles. With this, people without home chargers can charge their cars about once a week at a public or office charger, and even the automakers have some benefits. They can either make their vehicles go further, or they can downsize them and sell smaller vehicles. The impacts on the grid from a full EV replacement can either go unnoticed if it's planned well, or it could lead to catastrophic energy shortages, which would impact the overall global economy. New York appears to be better prepared with the mandates set by the CLCPA. With careful organization, grid capacity will be added. Additional legislation from other governments will make renewables more accessible and more affordable due to the effects of supply and demand. Additional renewable energy projects will be announced, and it will ease the concerns of meeting the energy demands of the future. Additionally, when combined with smart vehicle-to-grid technologies, utilities can incentivize spreading the load curve by rewarding customers for delaying charging. Furthermore, as the levelized cost of electricity of renewables decreases, the difference between peak, off-peak, and overnight peaks may even shrink, which can incentivize others to build chargers in places where people will be during the daytime. This will help move the load to be in sync with the peak daytime power generation, which is ideal. Finally, I learned different models produce different results. Modeling the real world for forecasting is very hard. Some models are not publicly accessible, open source models may require a large uplift, and I even experienced limitations with the model I used in System Advisor model with the wind turbines. I can only use 250, and then I doubled it to get the right value that I was looking for. Even that is just an estimate. This project was a good exercise to compare different models. And I also used a senior economist's prediction and compared that to my own prediction using public data and tools. Further refinements to these models will be made, which will eventually help make better predictions for the future needs of the electric vehicle grid. I'm just going to quickly show the works cited, 1, 2, and 3. And thank you for watching. I appreciate your time listening, and I look forward to a cleaner grid and electric vehicles in the future. Thank you, everyone, and have a great day.